Linear systems can be represented by vector equations. So vector equation form is another form for a system. First of all, I want to talk about vectors. So what are the vectors and what kind of operations we can do using vectors? So if I give you, for example, two numbers in a column. So for example, just some numbers here. And you can say this is a matrix with two rows only one column. So a matrix with only one column is called a column vector, or simply a vector. So this is a vector. A vector with two entries. Here's the first entry is 2, second entry is 5. And so each entry is a real number. It's very, very simple to look at. So now we can just see the operations. Operations is that we can do addition. We call it sum of two vectors. We can also do the constant multiple of a vector. So if you multiply a vector, certain vector x by c, so that is a constant multiple. So we call it cx. So it's just a notation. As you can see, we can denote a vector here by boldface letter. So now, what do we mean by adding two vectors? So we're very familiar with vectors in R2, that is a two-dimensional space, right? That means a vector with two entries. And then let's simply start with vectors in R2. How do we do sum? Yeah, that means addition of two vectors. How do we multiply a vector by a constant? That's called a scalar multiple. You see the terminology. So in this, each name is defined precisely. So we must know what do we mean by this term. The scalar multiple of a vector x by c. C is the scalar, this number. So the sum is simply add the corresponding entries of two vectors. Of course, the two vectors must be of the same dimension. So suppose one vector is in R2, then the other vector should be in R2 as well, because then they are of the same shape. Then we add the corresponding entries. So here is one example. So you can see that with this two vectors, we gave them names, x and y, the two vectors. So if we add the two vectors, what do we get? We just simply add the corresponding entries. So that is 1 plus 4. We add 6 and negative 3. Then we get a new vector. So the result is 5, 3. So you see in this sum of two vectors, just simply you add the corresponding entries of these two vectors. Now, scalar multiple. So suppose I want to do 3 times of vector x. So x is given. How can you multiply a vector by a number? But this is an operation that is defined as this. That is, each entry of the vector will be multiplied by 3. So 1 times 3, which is 3. 6 times 3, which is 18. So we have a new vector. As a result, 3x is a new vector. It is obtained by multiplying the vector x, each entry of x by 3, and then you get the scalar multiple of x. Okay, so these two very simple operations, just the sum and scalar multiple. So with these two operations defined, then let's try a few vectors in R2, and then we can just simply, for example, what is 3x plus negative 2y? So this operation is simply to find a scalar multiple of x, right? The scalar is 3. And so 3 is the constant. This multiple of vector x. And another multiple of y. Okay, y is given a given vector. So a multiple, scalar multiple of y, and then you do an addition, sum. So after this analysis, then we know what to do. So 3 times x, which we know already, negative 2 times y. So we can do just each entry of y times negative 2, we get a scalar multiple of y. And then these two vectors, we add them. That means we add these two vectors, we get a new vector. So that's negative 5, 24. So as you can see, after each operation, we get some new vector. So this is a new vector as a result of a sum. Another new vector as a result of scalar multiple of x, scalar multiple of y. We get each time a new vector. And also this is a combination, right? This is a, so 3x plus negative 2y, then we get a new vector. So we can generate new vectors with the sum and scalar multiples. Yeah, we can get many new vectors. So now if you can do the sum and scalar multiple, what is the geometric meaning of this operation? So let's see this picture. If you add any two vectors, so here x and y, if we show some given vectors x and y in the R2 space, R2, that means a two-dimensional space. So that means that, for example, yes, that means each vector in this space will have two entries. So to represent this x, as you can see, this x is just a 6, 0, right? To represent y, so here x is our both face. This is the vector, and the both face, the y is another vector, which is 1, 2. And when we do a sum, we get x plus y, the two vectors, x plus y, we add the corresponding entries, which is a 7, 2. 7, 2, so this is a 7 and 2. So as you can see, that's another vector, which is here. Yeah, it is a diagonal of a parallelogram. Yeah, that's the sum. So we can also see this. So if you draw the x and the y and then you form a parallelogram. That means you find the same y, which is the same vector y at a different location. You see, this is the same y, right? Because it is in the same direction, pointing to the same direction, same length. When we compare any two vectors, we say they are equal if they have the same length and they have the same direction. Yeah, when both length and direction are the same, then the two vectors are the same. So that's why these two are both y vector. And then the x is here. So then if we look at the x vector, and then this is a shifted y vector, and then starting from the starting point of x, and then pointing to the y, and then from starting of x to the y, then that is the sum. That's the x plus y. So this is x plus y, a vector from the here, the starting point to the tip of the y vector. And it is also a diagonal of the parallelogram. Right, if you form a parallelogram, you see this with x, x, y, y, and that's a parallelogram using the two vectors, x and y, the two vectors. Then you can discover the diagonal. That is the geometric meaning of sum. Then what is the geometric meaning of a scalar multiple? Scalar multiple, suppose I have a y here. So if we have the y, which is 1, 2, and suppose I multiply it by a scalar, which is, let's pick a number. I say 2, twice of y, of this vector. What do we mean by that? So we know the result will be a new vector, which is 2 times 1, 2 times 2. So 2, 4 is the vector. So if we draw that vector, we can see it is 2, 4. So will be here. So we will start draw this will be the 2, 4. Yeah. So this y is showing here, and 2y is simply twice as long as y, but in the same direction as y. So that means if I, okay, just make it more, this is a 2y. Same direction as y, twice as long. So as you can imagine, if it's a negative 2y, it will be pointing to the opposite direction twice as long. So negative 2y. Yeah, so we will be able to portray that. So it's just to show that for certain given vector, you can multiply it by scalar, and geometric meaning will be if it's a positive scalar multiple of y, then it's in the same direction as y. If it's a negative number times y, then you get a vector that's in the opposite direction of y. But the opposite direction, but it's twice as long. So it's just to get some interpretation of those operations. And we know we can do the operations now with the definition, right? As long as we define how to do the x plus y, how to do the scalar multiple, then we can extend the definition to a general case. The general case is a vector with n entries. Okay, so let's n. What is n? A vector with n entries. N can be 2. In that case, we will look at vectors in R2, two-dimensional space, and then we can have the sum and scalar multiple, and then do the operations using those to generate new vectors. But this n doesn't have to be 2. It can be bigger than 2. That is, we can still define the sum and scalar multiple similarly. For example, if we add 2 vectors of this form, then that means just simply get another vector of n entries and adding the corresponding entries. Scalar multiple is also defined similarly. So if we have a certain number, so the xy can be in n-dimensional space. That means each vector has n entries. N is a certain integer value. Yeah, that's the number of entries. And when we add 2 vectors, they must be both in Rn. Yeah, that means they must have the same number of entries. And then we can do the addition. This addition just means a new vector. As a result of this addition, then we simply add the corresponding entries of the x and y's. And scalar multiple similar. So a certain number times a vector. So if you have a number c, then c times each entry of vector x, you will get a new vector. So again, 2 operations defined as before, except here n is the dimension of the space. Now let's look at example in when n is 3. So when n is 3, that means it is the set of vectors we consider is the vectors with 3 entries, right? So 3 entries, so vectors of this form. So let's, okay, again, what do we mean by equal same? Whenever they have the same length, same direction. If 2 vectors have the same length and the same direction as well, then the 2 vectors are equal. And how do we do the sum? We just add the corresponding entries of the 2 vectors. How do we do scalar multiple? A scalar multiple of vectors x. So we just simply multiply each entry of x by this constant c. Then get the new vector, which is denoted by cx. So cx is a notation for that result of a scalar multiple. Okay, now let's look at the vectors here. We simply add them. Let's add 2 vectors. You see here the 2 vectors, one is called u, one is called v, and then we add the 2 vectors. What do? We just simply add the corresponding entries. So that's the sum of the corresponding entries. Then 2 plus 6, which is 8. 3 and 4, which is 7. So we add corresponding entries. What do we get? We get a new vector as a result of this operation of 2 vectors. And continue, we can do scalar multiple, right? So the u, which is the given u here, times a number, -2. So how do we do this multiple of u? This is a constant. So constant times u means we multiply each entry of u by -2. So 1 times -2, 2 times -2, 3 times -2, and we get this is the -2u. That so after this operation, scalar multiple, we get this vector. You see, each operation results a vector. Then let's do a slightly complicated operation. This is u plus half of v. Okay, so it's overall a sum, right? A sum of two vectors. So, but let's first write down the u, which is given. V is also given, but half of v. So let's do this scalar multiple, half of v. And once we get half of v, then we can do the sum. Yeah, we can do this addition, u plus this. So keep the u as is and figure out half of v. Half of v, that means this, right? Half times each entry of v, we get half of v. And then together, the sum will give a new vector, which is 0, 5, 5. So you see that's just a combination. Yeah, it's a sum of two vectors. So far, we worked with vectors in R2, vectors in R3 to show that we can extend the definition, and we have already extended the definition to sum and scalar multiple in Rn here. So n can be 2, 3, or even 4, right, etc. So we realize this form is very much the form is with given two vectors, we can, you see, one vector is u, the other vector is v, and you can do scalar multiple of u, scalar multiple of v, and then do a sum. So this is a certain vector because the scalar multiple of u is just a new vector, right? Scalar multiple of v is also a new vector, and then you add them together, that's another new vector. So this is a linear combination of u and v, two vectors. Yeah, so involving only two vectors. So we can recognize a certain form just to see what they possibly mean. So that's just another vector. Yeah, generated by u and v with those AB as numbers. So with the definition, we can easily verify the following properties. That means we have associative property. This is a commutative property. That means you can change their spots. X plus y is the same as y plus x. Yeah, due to the fact that we're simply adding the corresponding entries. Immediately, we can also verify that the associative property is true. That is, when you have three vectors of the same dimension in the same dimensional space. Yeah, three vectors of the same dimension, then you can add the first two first, and then add z, or you can add the last two vectors at the beginning, and then add the x. So it doesn't matter which one you do first. So this is called associative property. And then there's a zero vector. That means a vector with only zero values. Yeah, for all entries. So that's a zero vector. Zero vector add, that's also a zero vector in this. space in that Rn. So that means each entry of the vector is 0. So if a 0 vector is adding, we add 0 and x, then you get x. It's the same as x plus 0. It's still x. And there is also negative x. That means opposite vector, which is the same as -1 times x. Yeah, so this negative x is just a multiple of x with the scalar being -1. Yeah. So this negative x, if you use this negative x and you add x and negative x together, if you add them together, what do we get? It's going to be a 0 vector. Yeah, so it doesn't matter negative x plus x or x plus negative x, you always get a 0 vector. And if you have a scalar multiple applied to the sum, you get c times x plus c times y. So it's a distributive law of the scalar multiple onto each vector. And if you have the sum of two numbers times x, that will be the same as each number times x, and then you do the sum. So it's also a distribution of the two numbers onto x. Yeah, but it's you see both are distributive. It's the c onto each vectors, and this is the two scalars onto the vector x. And then if you have c times d, well, that you can really multiply the two numbers and then apply the product as a scalar multiple of x. And there's a very special scalar multiple, which is 1. If you use 1 times x, then it's going to be still x, because each entry of x times 1 is still the same as the original entries. So x will be the same. So these properties are very easy to verify. So if you want, you can easily verify. Let's pick one. Suppose I want to verify the d, right? So let's pick the d. Suppose I have an x, which is in Rn. So I want to add a negative x. What is the negative x? So negative x, it means the -1 times x, right? So -1 times x. So we know -1 times x means each entry of x times -1. So we can immediately get, so we know the second part is simply the negative x1, negative x2, negative xn. So the -1 times x is simply that. And then, so right now I try to show what is exactly the negative x. So negative x, as you can see, is same as -1 times x, which is this. And then x, let's copy the x. So x plus negative x, do I get 0? Yes, if we add corresponding entries, It's just the x1 plus negative x1, which is 0. x2 plus negative x2, which is 0. So we're applying the sum of two vectors, right? By definition of the sum, we simply add corresponding entries. So that's, yeah, so we have x1 plus negative x1, x2 plus negative x2, etc., xn plus negative xn. Of course, each one is a 0. Each entry is a 0. That's a 0. That's also a 0. That's also a 0. That's why we get 0 vector. This is 0 in, this is a 0 vector as a result of this sum. So we just verified using the definition of the sum and also definition of the scalar multiple. We verified this property D. You can choose one of the properties and try to check if they are true. Yeah, that can be proved. Last but not least, I want to remark on this. For example, if I have some operation, so let's just try to give an operation. For example, for the concept, so I have U and V in the R2 because it's very easy to draw. I'm going to use R2 as just a demonstration. So here I have a U. Suppose here's a U vector, and then I have a V vector. Okay, so suppose I want to draw another vector. So 2U plus 3V. So let's draw the 2U. The 2U will be twice long as U, just from the geometric point of view. So I'm going to draw the 2U. So the goal is I want to produce a vector 2U 3V, right? So this is U, but 2U will be, yeah. So I want to use a different color. So here, red. Oh, so this is just a bright color to show you the 2U is that one. Yeah, twice as long as U. So once you get 2U, and then I want to also draw the 3V. 3V is certainly in the same direction of V, but 3 times as long. So I'm going to use also a different color. So let's say 3 times as long, so in the same direction of V. So this is a 3V. So you see V here, 3V is this vector. So once we get 3V, then I'm ready to get the sum, right? Using the parallelogram rule, then we just draw the sum. So this is a parallel to 2U, and then this is a vector parallel to 3V. So this is a 3V, you see? And then 2U plus, so I just draw another 3V. 2u plus 3v will be this one. Oh, 2u plus 3v will be, we'll use diagonal. That is 2u plus 3v. Yeah, so here you see the 2u, and that's a 3v. So 2u plus 3v using the parallelogram rule. So this is a vector that is being generated by u and v. More specifically, by a scalar multiple of u and scalar multiple of v, and we get a new vector. And we call this vector just 2u plus 3v, but it is actually a very specific vector, right? Being generated by u and v. And we can also say a linear combination of u and v and produce this vector in the black ink I drew here. Okay, so now hopefully you have more intuitive understanding of vectors and vector operations and their geometric meanings. Of these operations.